Okay, today again we are looking at two-dimensional motion, in particular projectile motion. We will discuss another case which we have called case 2. Previously we looked at case 1, where the projectile was launched from the ground. But today we are going to have another scenario where we'll see where we're going to launch the projectile from, and then be able to use that scenario to solve the question. And so I urge you that you go back to the lessons that I've presented before, so that you can have the preliminary knowledge. Because in this particular lesson, I might not explain in depth how we came up with the equations that we are using. And so it's important that you go back to the previous lessons under YouTube that I've presented before, so that you can follow through. As you know, learning is actually incremental in nature. You do not just abruptly grasp a concept from the middle. So you have to start from the preliminary concepts and then develop them over and over until you cement them. And so here we go. As I indicated, and so the question reads as follows. A student throws a ball from the upper edge of 45 meters vertical building with a speed of 20 meters per second at an angle of 30 degrees above the horizontal, as shown below. And so in this question, we're going to look at a few aspects which we have discussed before, but the launch of the projectile is actually different from the previous one. So we're going to answer the question A, which is find the time for the flight of the ball until it hits the ground. So find the time it takes from this point here until the ball actually reaches the ground. This is thrown from a building. This is the building. The height of the building is 45 meters. And then part B, we are going to look at the components of the velocities at impact. At this impact here, just before actually the impact, what will be the velocity? The velocity, that is the X component velocity as well as the Y component velocity. And then part C will also calculate the actual velocity now, the resulting velocity or resultant velocity that will result at impact. And finally, we will also calculate the horizontal range, that is the distance from the point of launch here up to where the ball actually hits the ground. This is the range. And so we will look at now part A. Part A, we find the time for the flight of the ball until it hits the ground. And so you are very much aware of this equation, which is a one-dimensional equation, which is actually used at high school level, where we say displacement is equal to initial velocity times time plus half times acceleration due to gravity g, and the t squared, which is time squared. And so when you are calculating the time in 2 dimensions, we use the equation for actually displacement in the y plane, which is y is equal to y initial plus the y component times time minus half acceleration due to gravity, which is g, and t squared. The minus here indicates that the ball is moving against gravity. It's moving up. which I've simplified here, where we said VYO, which is V initial, Vy initial, which is the component. The component in the Y direction is velocity initial times sine theta. Okay. And so this is the expression that will enable us to calculate the time. As you are aware that this ball here, its initial position is, which we have called y0, is this point here. And therefore, it is dropping down in the negative y-axis. And therefore, we say y0 is, y initial is actually 0. That point where it is starting from, it is 0. And therefore, we have to remain with the y, which is in a negative y-axis. And you note that actually that one is given by negative 45 because it's in the negative y-axis. Plus 0, this is the y initial where the ball is starting from. And then you have 20 meters per second as the initial velocity, sine 30 times time minus half times 9.8 times t squared. And so what we have developed here is a quadratic equation. So we can take this negative 45, this side becomes positive. So we have come up with a quadratic equation, and we know how to calculate equations using the quadratic equation. And so this one becomes minus b squared, and then this is b squared, and then this is 4 over 2a. And so you substitute here where there is b, this is the one we are using here, minus 19.76. And so this one becomes positive, plus or minus, and you square b squared, which is 9.76 squared, minus 4 times our a here, it is negative 4.9, which is this one. And our c is 45, positive 45. And you divide everything here by 2 times a. Our a here is negative 4.9. And so when you simplify this equation, you actually get 10, you get your time as 4.2 seconds. So that's the time. So it means that we have calculated the time of the flight. That is the time from the point of launch here until the ball hits the ground. So this is the time, which is 4.2 seconds. The second part of the equation, we will look at the component velocities at impact. So you note that the x component does not change because it is not actually affected with time or by time. And so we say velocity in the x component is v initial cos theta, which is 20 times cos 30, which is 17.3 meters per second. So at every point, the velocity component will be the same in the x-axis, while in the y-axis, it will vary with time. So our equation is Vy component is equal to V initial sine theta minus acceleration due to gravity times time. Then we just substitute the figures here. So for the initial velocity, we have 20 meters per second, sine 30 degrees minus 9.8 as the acceleration due to gravity times 4.2 as the actually the time for the flight. okay, the whole flight minus, so which is equal to 10 minus 4.116. So this gives us a 31.2, negative 31.2 as our velocity in the y component. So number C, we find the Bose velocity impact. Using the same velocities we have been given, you can actually draw a diagram showing that the 17.3 meters per second is a vector in the positive x-axis, and the other component in the y-axis is actually negative. Remember, we found negative 31.2, so it has to move in the y-axis, which is 31.2 meters per second, which is negative. And so for us to enable us to find the velocity, we merely use Pythagoras theorem, where we're saying this resulting velocity, which is v squared, is equal to 17.3 squared plus 31.2 squared. And so the velocity would be equal to, using Pythagoras theorem, you can actually square the whole of this and you get 35.7 meters per second. And so it means that we have found this resultant force at impact. So if we are also to find in a vector description, it means that we have also to look at the angle. So the angle with the horizontal, with the x horizontal axis, this is the angle here. And so we can use tan theta is equal to 31.2 over 17.3, which gives us 1.8. And therefore, the inverse of this, theta, for us to enable us to find the angle, theta is equal to tan inverse of 1.8, which is 60.9 degrees, with the which is actually with the positive x-axis, meaning that this is the angle where it is up to the positive x-axis. It is that angle, which is 60.9 degrees. Finally, we can find the horizontal range of the ball. The horizontal range, we merely find the distance of the ball from the point of launch up to where it hits the ground. In other words, we are calculating from the diagram here, we are calculating this distance from the point of launch here up to the point where the ball hits the ground, this distance here. And so you merely, when you are looking at the range, since the range is all about the movement of the ball in the x-axis, therefore we are using this equation for the x-axis, where we are saying x minus x initial is equal to v initial cos theta times time. Actually, the x initial, which you said x O, is this point where it is starting from, and then this is x. So you have to subtract x minus x initial, and it gives you actually the range times so x minus x0 is equal to v initial cos theta times time, and we know the velocity, which is 20 meters cos 30 times 4.2, which is actually the time for the complete flight of the ball from the time of launch, from the point of launch to when it hits the ground. And it gives us 72.7 meters. And so this is all for today. I hope you have enjoyed the lesson, and I encourage you that you subscribe to my YouTube so that you can continue getting knowledge from this lesson that we are actually presenting. I thank you.